All right, so now we're going to look at 9.2, which involves the comparison of two means. So first thing is that when we compare two means, we're going to use t instead of z, so that's going to change a few things. And of course, means use different formulas than proportions. So our test statistic, again, is now a t value because we're using means instead. And so that's going to give us this formula right here. Our confidence interval formula also then changes. One thing to notice, though, is that this time, when we compare two means, the standard deviations don't change this time. So the z's, again, the two proportions, use this combined c, and again, we have a calculator, so that's not quite a worry as long as we know how to use our calculator. But the means use the same standard deviation, whether it's a test statistic for a hypothesis test or a confidence interval of those two proportions, which is a little bit interesting. So with that being said, we've done a lot of the heavy lifting. The thing we'll have to review as we go through this is how do we deal with that critical t-value, or how do we use that t-value, and it's based on degrees of freedom. But everything else about the wording, the concluding, is 0 in my interval of my comparison, is the p-value less than alpha, that all remains the same. It's just really working with these two new formulas. So with that being said, let's dive into 9.2 and do the homework. Okay. So here's 9.2. All right. This first question is a little bit weird, but it makes sense, and it's something that actually still we need to worry about in 9.1 as well, and that's that the two samples we select should be distinct from one another. And so this first question says, if I've got one sample of college students and another sample of teachers, are those distinct or not? And I think we're going to end up saying that they are distinct or independent, because if you're a college student, you're probably not a teacher. I mean, I don't know, there is a rare subset where there are people who are in college, maybe they're getting their doctorate, but they're currently a teacher, or maybe they're working on their master's and they're currently a teacher, like myself at one time. But I think we're going to say they are independent because there is not a natural pairing between the two samples. I think what that's saying is, we don't think that these two are going to overlap at all. Cool, and my guess was correct. All right, up next, we dive into question 2, and it says, hey, here's the 95% confidence interval for the difference between two populations. So they've kind of glossed over telling us about the individual data. They're jumping right into what we last saw in 9.1, which was if you have a confidence interval, how can you utilize that to still make some same conclusions like you would in a test? So my confidence interval, what I'm noticing, has negative values to the left of what I expect the true difference between these two to be, and negative values to the right. So in other words, that means this subtraction or comparison is one-sided. It always, with 95% confidence, results in a negative value. Well, what does that mean? Well, if your subtraction results in a negative value, then the second value had to be bigger, all right? That's how you get negative values in subtraction, if the second value is larger. So that's what this confidence interval is saying. 95% confident that the second interval, or the second population, so women and men, which one came first? The men correspond to population 2, so we're 95% confident that the hemoglobin level in men is going to be larger than for women, because the subtraction between the two, the comparison between the two in a confidence interval is always, or is sided towards the negatives. Okay, because it does not include 0, it appears that there is a significant difference between men and women. Great. All right, write a brief statement that interprets the confidence interval. We're 95% confident that the difference between the two population means is either those values. No. 95% confident that the interval, there we go, looks like D. So why is it not A? Because we're not there to say what the value is exactly. It's not either the lower bound or the upper bound. It could be anything in between those bounds. So we're never going to say exactly what it is. We're also, we cared with 0 in the interval to see if this was one-sided or not, but the confidence interval isn't about 0. Why is it not C? Because C essentially says the right beginning statement, but then says does not contain. But here we go. We're 95% confident that this range that I found does contain the true value. And again, that's why we were able to conclude that there is a significant difference, because if I think that the true interval is somewhere between these values, then I think that the true mean of these two, or this true interval, is always negative, because the second population is always larger, so there is a difference between them. All right, part C. express the confidence intervals with men being population 1 and women being population 2. So in other words, what happens when we switch men and women in the subtraction order? Well, we should get the same values. It's just that these signs are going to be switched. So if the signs are going to be switched, well, then now the 1.62 is less than the 1.76. Because if the men go first, then now the subtraction is larger minus smaller, which is always positive. All right. Up next, now we're going to actually dive into a test. So we've got treatment group, placebo group, and that's what we have about them. So what's the null and alternative hypothesis? It is, let's see here. I think we're just going to test that it's not equal to, because it doesn't kind of tell me in the wording what I'm trying to do. And so this is an error that a lot of students make. A lot of students make the error of noticing, hey, the treatment group's average is less than the placebo group. So the null must be that the treatment group is less than the other. But you don't get that from what the sample says. We get that from what the wording of the question says. So even though it does look like the first is less than the second, this wording just essentially indicates that we just want to see if they're the same or not. So not equal to. All right, so again, you get the alternative from the wording, not from the data. Now the question is, what is the test statistic? And we're going to run through the formula by hand just once, or in other words, not using the cheat, so to speak, in the calculator. So it's going to be, when we're doing the mean of the men. Actually, I'm just going to type it in the calculator as I go, because there's no point of me typing it in and then, or writing it and then typing it in. So the average from population 1 minus the average from population 2, and that is ultimately getting compared to 0, but we don't need to write minus 0, because when you subtract 0, nothing really happens. We then have the square root of, and I'll make a few more fractions here, another fraction plus another fraction, and it's standard deviation 1 squared divided by the population size of 28 plus standard deviation 2 squared divided by population 2. All right, and there's my test statistic, negative 1.74 when I round that to 2 decimal places. All right, and now the question is, what's the p-value? And we're going to do the hard work of calculating the p-value. Let's see here. I think what I'm going to go for is I'm going to use the conservative degrees of freedom, which means make your degrees of freedom based on the larger population. So let's see here. I've got degrees of freedom essentially 40 then. Degrees of freedom essentially 40. And my test statistic was negative 1.73. So what I'm going to do is I'm going to find on this table where's 1.73 between, and it's between these two values. Now let's see, they want the p-value precisely. So actually, you know what, we can't really do this by the table. We're going to have to do this using the calculator. So here's what we're going to do. We're going to go to distribution, and we're going to go to TCDF. And be careful, because we were doing a not equal to test. So let's kind of get this out of the way. Let's see what we found. We found a t-value of negative 1.74. There's 0. So I'm going to find the area less than 1.74, and then of course I'm going to double it because this is a not equal to test. It could have just as been likely that it was going to be positive. All right, so that means the first thing I'm going to do is find this left-hand side. So the lower limit is negative huge number. The upper limit is that test statistic value I found, which was negative 1.74. The degrees of freedom I'm going to use is, I guess, 39. That's called the conservative degrees of freedom. Now, the computer might tell me I'm wrong. They might use not the conservative degrees of freedom. They might do something else, but let's find out. To 3 decimal places, I get 0.045. All right. So what did they do for their p-value? So here's what I'm going to say. I'm totally okay with this. I think that's going to be perfectly fine. I just want to see what happens maybe if I don't know, just use maybe 30. Just go in between. I get 0.046 now. Interesting. Oh, sorry, because I have to double it because it's two-sided. I'm so silly. So I found that value. Let me double it. And now let's round it to 3 places. Third time's the charm. Better be right. It's going to round to 3 decimal places all the way to 0.090. There we go. So we were right the first time. We could have used the conservative degrees of freedom. I forgot to double it at the end. All right. Again, careful about a two-tailed test and doing this by hand. Or in other words, I just gave you a really good argument for why you should just use that calculator menu, and we'll go through that. Okay, the p-value is 9, which is kind of big. Usually we want less than 5%, but this time the significance level was 10%. So in other words, I get a result that would only happen by chance 9% of the time, and I'm only going to reject if I get a result that's rarer than 10% of the time. Well, mine is less than 10%. It's 9%. So I will reject the null hypothesis, and we can reject the claim that they have the same mean. Or in other words, we can reject the null hypothesis. All right, now they want me to do the confidence interval, so here we go doing the interval. I'm just going to kind of type it in as I go. 2.37 compared to 2.68. We'll do the minus. Now I need that critical t value. So I'm doing a, let's see here, let's talk about this t value. I'm doing a 90% 1 minus alpha, 1 minus 10 interval. And if I'm doing a 90% interval, then that means there is 5% in either tail. So I'm looking for tail probability of 5% because this only tells you one side. And again, I'm going to use the 5%, and I'm going to use the degrees of freedom of, I guess, 30 or 40. Somewhere between those two. I'll use the conservative degrees of freedom, and again, let's see here. Oh yeah, there's 90% confidence right there. I guess I'm going to use the bottom value. So between 30 or 40, I'm going to use 1.684. All right, 1.684. I guess really ideally, 39 lives somewhere between 30 and 40, so maybe I could come up with a number somewhere between these two really small, but it won't make that much of a difference, I don't think, by the time we deal with the whole square root standard deviation stuff. Now we have the square root of, again, standard deviation 1 squared, which is 0.82 squared, divided by its sample size, which was 28, plus the other standard deviation, 0.56 squared, divided by its sample size. And I get that for my lower value. And to 3 decimal places, it looks like that would round up. And now I'm just going to copy this whole entire thing because now I need the positive value. Or rather the positive t in between, which still is negative 0.009. Now, again, I just feel like this is going to be wrong because I'm using the table, but I was right, so cool. All right, really quickly, again, let's run through what this would be using the calculator and show you just how easier that would be. We're going to go to tests. This time we are doing a 2-sample t-test because we have 2 samples, and we're going to input the data via stats because we have those summary statistics. So the mean from one was again 2.37, the standard deviation was the 0.82, the sample size was the 28. For the other, it was 2.68 for the average, 0.56 for the standard deviation, and 40. We were doing a not equal to test, and pool is going to be set to no because we're pretty much always going to have that set to no. Look, there's the t-value of negative 1.74, and there's the p-value that actually, again, because of the higher degree of precision, doesn't round up to 0.9. So that's a little bit interesting there. So this would be correct. Again, on my test, I do not care about this being 0.089 or 0.9. It's going to be the same effect. The calculator, being more precise, has somehow found a value that wouldn't round up to 0.9, but that is okay. We still would have the same conclusion, though, because it's still less than the alpha of 10%. Let's then make the confidence interval. So a 2-sample t interval, there it is. And thankfully, all the same data is already there. This time we wanted to be 90% confident. 90. And there are those values. Once again, because of the higher degree of precision, it comes out a little bit different, which is just a little bit interesting. So there we go. All right. I'm actually curious. We've got some time. I'm curious to see what they do about the degrees of freedom. All right. They just say from using technology. Interesting. Okay. So they don't really say how they're getting that exact value from the calculator. So just be careful about the fact that we can get some little insignificant rounding errors that don't interfere with the entirety of the question, but might give us a little bit of variation in our answers. And in fact, maybe the computer system allows a little bit of variation in their answers as well.